Hello, I'm Ridula, and this is my Physics 2111 lab, Experiment 5 Falling Slinky. The purpose of this experiment is to first use the tracker to track the observed motion of the falling slinky, and to use the computational model to predict the ideal motion, and to compare both models. Then to find out if the bottom of the slinky remains stationary in the model. A preview of the main result is that the bottom of the slinky remains stationary. The first principle I used is Newton's second law of motion, which states that the rate of change of momentum of a body over time is directly proportional to the force applied. So the net force is equal to the spring force plus the gravitational force. The drag force is negative b times the magnitude of the velocity squared times v hat. And the gravitational force is F-grav equal to negative mg j hat. So initially when the net force is 0, when the bottom of the slinky is stationary, the tension force is equal to negative times the gravitational force, so which is mg j hat, and then I also use the velocity and position update formulas. So here I used a tracker to track the motion of the falling slinky. So I calibrated the video with the calibration stick and both the axes. So the system is the spring, mass, and earth. The surroundings are nothing, and the initial conditions are the position. The starting position is 0.05012 in the x direction and negative 0.71 in the y direction. The initial velocity is 0, and the mass of the slinky is 0.218 kg. So if you look on the right, from 0 to 5 seconds, the line is stationary, as that's when the bottom of the slinky is stationary as the top starts falling to the bottom. And after 5 seconds, it decreases as the bottom of the slinky is no longer stationary, as there's also a drag force along with the force of gravity, and the net force is also no longer 0. This is my code in GlowScript, and these are the initial conditions. The mass of the slinky is 0.218 kg. The initial position is 0.05012 and negative 0.71, and the velocity at the starting point is 0. Delta t is 0, and delta t, the time step, is 0.033. That's the value I used in my tracker. And then there's g, which is 9.8, and I calculated b, the proportionality constant, by trial and error, and I got 92.35. So this is the first while loop when the bottom of the slinky stays stationary. So 5 seconds is how much time the bottom is stationary for. And there's two forces acting on the slinky, which is the force of gravity and the tension force. So since the net force is 0, the tension force exerts an equal and opposite force to the force of gravity. So Ft is equal to negative W, and F net, which is 0, is equal to the weight plus the tension force. And next are the velocity and position update formulas to update the slinky's velocity and position. So this is the second while loop when the top of the slinky reaches the bottom and the slinky starts falling down. So the net force is no longer 0, and there's also a drag force with the force of gravity. So the net force is the weight plus the drag force, and we also use the velocity and position update formulas to track the slinky, the position and velocity of the slinky over time. So this is the model comparison. So in the graph, the orange line is the computation model and the blue line is the observed model. So as you can see, from 0 to 5 seconds, they align, and then towards the end, when the slinky starts to fall down, the computation and observed model start to deviate. Next is the sources of errors. So the first error is the tracking error, where the placement of the point of mass may not have always been at the center of mass of the slinky. And the second one is that the observed motion of the falling slinky has fluctuations due to external forces not accounted for. So in discussion, the first question is, why does the bottom of the slinky remain constant when the top is falling to the bottom? So the force of gravity acting downwards is balanced by an equal and opposite tension force due to the slinky. The second question is, after the top reaches the bottom of the slinky and the slinky starts falling down, why is the base not stationary? So once the top reaches the bottom of the slinky, there's no tension force. And there's also a drag force additional to the force of gravity. So the base of the slinky is no longer stationary. Thank you.